we can exchange our thoughts and the progress or the advances which has taken place in the field of engineering. Yes, ma'am.
First, Vinod sir will speak.
Yes. Vinod, you can carry on. Just it was a formal discussion with Professor.
Good
You
morning
can.
to one and all present gathered here in this 5 days FTP program. First, I introduce myself, Dr. Vinod Kumar. I am working as an associate professor in the Department of Computer Science and Engineering, MBJ College of Engineering. I would like to invite our principal sir, Dr. Mahabalishwarappa, to give the welcome address.
Thank you. Today, a good morning a pleasant morning to everyone who are connected to this, the 5 days, the faculty development program on artificial intelligence and machine learning. On behalf of the institution, on behalf of the management, particularly on behalf of the organizing department, computer science and engineering, I'm extremely happy and extend a very hearty and warm welcome to the speaker of the occasion, Dr. Biplab Sikdar. Sir is working with the capacity of the associate professor and vice dean, graduate programs and area director, communications and networks in National University of the Singapore. We are extremely happy and very fortunate to have connected with such a the experienced and vast experience is very much required, and we are very fortunate today to connect with such an eminent personality. We are honored to have you with you, sir. I extend a warm and a pleasant welcome to you, sir, for this.
Thank you very much.
As a speaker of the occasion. Organizing an event, it is not that much easy. The program also, it needs and minute look into all aspects. Organizing an FDP for a period of 5 days, it's a very big the responsibility. That responsibility it has been shared and handled very beautifully in a sequential way. And I'm extremely happy on this occasion to extend a hearty welcome to Professor and HOD of the Computer Science and Engineering Department, Professor Kaveshri Madam, and her team. And she is the leader and the front line in organizing all the events and the programs and the conferences and particularly STTP and the FTP, which are so essential component for the faculty to know and expose to the new things in the new areas and what latest things in the developments is happening across the world. So I welcome you, madam, on this occasion. I extend a warm welcome to all the professors, associate professors and assistant professors and all the heads of the departments to this the program. I welcome Professor M. Brunda, Vice Principal of our institution, and Madam is the inspiration and the backbone for all the programs which is happening in our campus. And because of the right at the support it has been extended by all these authorities, the Department of Computer Science and Engineering could able to organize so frequently the required number of the programs, which is very much essential and required for the faculty members. On this occasion, on behalf of all of us and the participants, a delighted welcome to you, madam. I extend a warm welcome to Professor Vaman Bigudi. Sir is the registrar and controller of examination of our institution. I welcome you, sir. Now, as the formal note on the program, from the last 1 decade, when we start looking, it is not too far. It is not a big history. Now it has gained a lot of importance, about 1.5 decades or max of 2 decades. The life of every human being, it has become so simple, become rich and comfortable because of a lot of revolution that has been happened in the area of the computer science and electronics. Because of the softwares and the other components, which made the man to lead the life so comfortably and in a more easy way. Without the computers and the software, day will not begin at all. Now this the CSC department has rightly chosen this topic, the 5-day FDP on artificial intelligence and machine learning. From the few days when we look at today's scenario, as our daily needs and requirements are increasingly increases with exponentially, and to meet our needs and requirements, as well to make our life still much more comfortable and happy, these the computer science and the field of computer science, especially the word artificial intelligence, has played a very prominent role, key element, and and AI and ML. This is the term has been gaining very much popular because of the recent the advances in the field of artificial intelligence and machine learning. So that the machine learning is always a sphere of artificial intelligence where the machines are responsible and able to perform and believed, and it is a special feature of the artificial intelligence and the machine learning, and it is nothing but a smart humans, robotics, and integration with the IoT devices, various IoT devices, has made machine to think in a right way and to work on the whole to meet the needs and requirements of the human being. When we look at the day by day, the importance of the artificial intelligence and the machine learning, even in the industry as well as in the academic, the scenario and the segment has been increasing. Very growing companies, almost all in the growing and frontline industries, are using these technologies to improve the purpose behind this, going with an IA and ML to improve their products and the kind of services they can able to provide to the customers, to evaluate the various business models, and to enhance their also the decision making at right time and the process to have a better and good control over the process. Always
Principal sir. Principal sir, sorry to interrupt. You are muted.
now you can hear.
Yes, sir. Audible. Thank you.
Okay, nice. Most popular the examples of the artificial intelligence which we come across in the recent days, and everybody knows that it is the self-driving cars. So the basic headline difference between the A and ML is the artificial intelligence includes all kinds of the systems and the methods and the robots performing intelligent actions. ML is only focuses on the AI methods and its applications. So let us hear from a speaker, and we are going to enlighten on more on the in-depth in all possible dimensions on this topic. Today, we are honored to have such a personality with us in the 5-day program. Now, I thank the organizing team of this 5-day FDP program for inviting me to inaugurate. I'm extremely happy to a part of this inaugural address and to be with you on this the inaugural the program of the particular the FDP program. I wish that on behalf of the management and the institution, all participants are going to be get a lot of benefits out of this 5 days program. So it should be an interactive program also. It should not be a one way. And I request kindly all the participants, and the participants, maybe the students, maybe the faculty from the other institutions, kindly have an interaction. When we have an interaction, then only we can able to extract more and more the useful and the recent information about the topic. So thank you for giving me an opportunity on this occasion to speak a few things on connected to this the FTP program. I wish this program is going to be beneficial and more successful one. Thank you very much.
Okay. Thank you very much, sir, for giving your continuous support and your encouragement and being a part of it as part of with us. And
Thank
I
you.
request Professor Kavya T. Ma'am, Head of the Department Computer Science and Engineering, to invite the guest and give the introduction about the chief guest.
Good morning, everyone.
Good morning.
Morning, sir. It is a great honor for me to introduce and welcome the chief guest, Dr. Biplab Sikdar, to the 5-day faculty development program on artificial intelligence and machine learning. Dr. Biplab Sikdar is the Vice Dean in charge of graduate programs in the Faculty of Engineering at the National University of Singapore, NUS. At NUS, he also serves as the Area Director for Communications and Networking and leads the research on IoT and cyber physical system security in the $30 million NUS Singtel Corporate Research Laboratory. Sir holds BTech from Northeastern Hill University, Shillong, MTech degree from the Indian Institute of Technology, Kanpur, and PhD degree from Rensselaer Polytechnic Institute, Troy, New York, USA. Sir is an expert on security protocols and computer networks, cyber security for Internet of Things, and cyber physical system, and has published several book chapters and more than 200 research papers in related areas. Sir is an associate editor for the journals like IEEE Transactions on Mobile Computing from 2014 to 2017, IEEE Transactions on Communications from 2008 to 2012, and IEEE Open Journal on Vehicular Technology from 2019 to present. And Sir is also a journal reviewer for various IEEE journals. And Sir is a recipient of Career Award from National Science Foundation, USA, the Tan Chin Tuan Fellowship from NTU, Singapore, the Japan Society for Promotions of Science Fellowship, and the Liv Erikson Fellowship from the Research Council of Norway.
Yes, sir. Welcome, sir. Welcome, sir.
Individual Contribution Award, WiMAX Forum, San Jose, CA, USA, Teaching Excellence Award from the School of Engineering, RPI, Troy, New York. Charles M. Close Direct Doctoral Prize, RPI, Troy, New York. ECSC Departmental Service Award, RPI, Troy, New York. Sir has been invited as a keynote speaker for various international conferences and workshops. Sir has obtained more than 32 research grants. Sir has guided more than 15 PhD students. I think this is a very short biography, what we can tell. Sir has pages of publications. So we shortened it for the time being. And sir, it is a great honor to have you on this day. Thank you.
Thank you very much for the very kind introduction. And also thank you very much for inviting me to talk here today. So I will get started then. I hope you can see the screen.
Yes, sir. Yes, sir.
Okay, great. Thanks. All right. So what I'll do is for the next hour or so, maybe roughly there, I'll talk about machine learning for IoT. And specifically, I'll talk about opportunities and challenges and so on. So I'll keep the talk at a fairly high level, so maybe not very technical till the end when I go into some challenges for machine learning and so on. Okay. Now to get started, so this is the agenda. We'll talk a little bit about IoT, and then I'll talk a little bit about machine learning and artificial intelligence. Since this is the first talk or presentation in the whole 5-day program, So I thought I'll just start with a quick introduction to machine learning and so on. And then we'll talk about specific applications of machine learning in IoT. And then I'll talk a little bit about security issues and challenges. Okay? So let's get started with IoT. Mm. So this is, the internet. IoT stands for Internet of Things. So the first word is internet. And internet started about roughly 51 or so years ago. And when it first started in 1969, there were only 4 computers in the whole internet, and they were all in the US, and also they were all sort of in the western part of US. And back in the day, people didn't have their own personal computers or laptops and things like that. Those things didn't exist. So a big organization such as a university may have a single mainframe computer, and people would remotely log into that computer to execute their jobs. So, you would log in and enter your password and so on. So the first thing you would do in such a case is you would type login, right? You would say L, then O, then G, and so on. And in this case, they sent L, they sent O.
I request all of you to mute your mics. Request participants. Hello. 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 Special request with all the participants. Mute your mics.
Make him as an, through MD to admin login, it is both.
Arvind.
That is the problem. He couldn't make. I'll manage.
Arvind.
Yes, sir.
Arvind.
Yes, sir.
Kindly mute your mic. Mute your mics, please. I request everyone to mute your mics. Lot of disturbances. Now it's okay.
Okay, great.
Kindly.
Yeah, thank you. So yeah, so first time people were sending anything on the internet, they were trying to remotely log in. So okay, so they sent an L and an O and a G, and then the whole system crashed. And this is the very humble beginning of internet. And if you see this person here, his name is Leonard Kleinrock, so he's considered as one of the fathers of the internet. And this big thing here looks almost like a refrigerator. This was the first router on the internet. And from such a beginning, we have come to expect new, technology has advanced so much that, the internet has become a very integral part of our everyday lives. And this one just shows how the number of nodes in the network increased over time from 4. And now we have like billions of devices on the internet. And back in the day, common applications were Telnet, where you remotely log into a computer, email, which started in 1971. And within 2 years, it was about 75% of all the network traffic. There were other protocols such as for transferring files, voice over IP kind of applications, and so on. Okay. And the whole popularity of the internet came in the early 90s when Tim Berners-Lee invented HTTP. Before the early 90s, most of the users, actually almost all the users of the internet were people in academia, professors, students, and so on. Or maybe some people in the military would use the internet. Regular people, didn't use the internet. But that changed with the invention of HTTP, which made looking and searching for information much, much easier. And that in turn led to a number of different applications which are very popular now: social media, sharing economy, internet commerce, and so on. Okay? So another way of looking at things is how the internet, the flavor of internet evolved over time. So before the internet, let's say 80s, 70s, and so on, we had telephones. And then the conversation was mainly human to human, right? You would call somebody or somebody would call you and so on. The early part of the internet, so in the 90s and so on, we call it sort of the internet of content. Here, mainly you would use the internet for looking up stuff, looking up information, reading web pages, reading news and things like that. And very soon people figured out that you can actually provide services over the internet and make money So e-commerce started becoming popular. So this is late 90s, early 2000. This is when companies such as Amazon and eBay, they got started and they started becoming popular. And then in the mid 2000s or late 2000s, it became the Internet of People. And this was mainly driven by social media. So around 2007 or so, 8, that's when Facebook, YouTube, applications like these become popular. And now we are in the era of Internet of Things. So what is the main difference? The fundamental difference here is, if you look at all of these, right, previously, at least on one side of the connection, there is a human involved, right? So in the Internet of Content, it's a human who wants to access the web for downloading information. In the Internet of Services, maybe on one side there's a server, but on the other side there's a human who's trying to buy something or get some government service on the internet. And even with the Internet of People, with social media, it's a human who wants to watch, let's say, go to Facebook and read somebody's profile, or go to YouTube, download a video, or it's a human who's uploading a video and so on. So all of these, at least a human is involved. But with Internet of Things, humans don't have to be involved anymore. Now our computing devices have become smart enough so that they know on their own when they need to transfer data or when they need to consume data, right? So they can generate data, they can process the data, and they can make sense out of the data and take action based on that data, right? Just as an example, if you think of an electricity grid, power grid, and you have the generators like diesel or hydroelectric power plants and so on. Then you have a transmission network. You have the transmission network, which will take the power from these generators and bring them to residential areas or factories or offices and so on. And at the end, you have the transmission, the distribution network. One of the main goals of a power grid is that you want to manage the supply of the demand of electricity with the supply. So you want to match that. You know, in the old days, even now, I guess in most places, somebody comes to your home and takes a meter reading at the end of the month, and then they give this meter reading back to the let's say the grid owner or the generators, and they somehow try to guess from that how much power you need to generate. Right? But then if you think about this, the amount of electricity we need is not constant during the day. Maybe at nights, the residential consumption goes up, but during the day, factories and industrial sectors, they start consuming more. So the amount of power we consume over the day, it varies over time, right? It's not a constant. So now we are coming to the era where we have smart meters that we can install at home. And these smart meters can, send back the report of how much power is being consumed every minute or every 10 minutes, every half an hour, however you want to set it up. So as a result, now we have a much better view of what's going on in the grid, and we can do a much better job of matching the supply with the demand and so on. So this is one example of where, automation, actuation, all of these things can be managed using the IoT. And these are some example domains where IoT is useful and is being taken up. So currently, this is 2018, but I think it's still the same, more or less. So the biggest adopter of IoT-based technologies is in the sector of smart cities. So here we are trying to do things like, smart buildings, smart environments, and so on, followed by connected industry, buildings, cars, energy, and things like that. So there's a lot of potential for IoT in various domains. And another way of looking at the whole thing is that if you look at the market share that IoT would have, let's say in another 4 years or so, IoT will have, this is a huge amount of money. So IoT has a lot of potential. Right? So let's take an example of some typical IoT devices and applications. So this is an example of underwater monitoring, and this is somewhere off the coast of Australia. In the Great Barrier Reef. So these yellow things are buoys, and what they have is they have a big wire hanging down here, right? And what that wire has is a large number of sensors, and these sensors monitor things such as, the algae content, the oxygen level in the water, the direction in which the water current is, and so on. And the idea here is you can monitor the health of the coral reefs and other things in the in the ocean. And they have these antennas up here, so through which they can relay the information. And there are small solar panels here by which they can be powered. Another example here is an or a smart pill dispenser. Many patients, especially if they're older, they don't remember when to take their medicine or how many medicines to take, and so on. So this device is quite smart, and this monitors how many pills have been taken out and whether they have been taken out in the right time or not. And if the patient has not taken his or her medicine at the right time, then it can send a message to, let's say, a relative or the doctor or the nurse or whatever it is. IoT devices are becoming increasingly common in factories. For example, robotic arms and so on are increasingly being deployed in factories such as car manufacturers and all kinds of industry and so on. Right? And here's an example of an application of IoT devices in agriculture. So here you have an IoT device, and you can put these two things around the fruit. And as the fruit grows, it'll monitor things like, how fast it is growing, what is the color, and so on. And as a result, you can tell if that part of the field needs irrigation or fertilizers and things like. So there are all these IoT applications and potential, right? So now, leading to the intersection of IoT and machine learning, one thing we would like to see is, where did IoT evolve from? So 20 years ago, 22, 23 years ago, people started working in the area of sensor networks, right? And here the idea was, at the time, advances in semiconductor manufacturing and sensor technology and so on had advanced to such a level that we were capable of making very, very small devices, which were capable of, this whole device is comparable to the size of a few coins. So we were capable of making these miniature small devices that were capable of sensing the environment, getting some data, and then send it out using a wireless network. Right? So, and as a result, people started believing that there were a lot of different applications. So IoT is essentially a continuation of that journey where we started with sensor networks, but now we have some additional ingredients in there. So this was a typical wireless sensor network architecture, and where your sensor would either directly communicate with a cellular or Wi-Fi base station, or they would form a multi-hop network in order to get to the gateway, which will then take them to the cloud. So 20 years later or 15 years later, what is the difference, right, between IoT and these sensor networks? So first thing is that, when we think about the scale of IoT, it's much, much bigger. So we expect sensor networks where more of specialized networks for doing one specific thing. And when we think about IoT, we think that they'll be pervasive everywhere and they'll be deployed everywhere. And the number of IoT applications is expected to be much, much more diverse and so on. And the other things are like, connectivity and automation and so on. But the big thing is this: the amount of data that we have been able to gather and label over the last 20 years, and the ability to analyze that data, right? So that's really what has changed. And there are two aspects to this. There's a hardware aspect and there's a software aspect. In terms of the software aspect or the computational aspect, the last 10, 20 years have seen a significant improvement in our ability or our understanding of areas such as AI, machine learning, and so on. Now, when we talk about AI and machine learning, the whole fields are not new as such. People were talking about artificial intelligence back in the 50s and 60s, right? So that's when people started talking about these things. Even, the biggest example of a AI technique or a machine learning technique is what we call neural networks. So people were talking about neural networks back in the 60s. However, what has happened is that back in those days, people didn't have two things. They didn't have very, very advanced or very powerful computers. And then for most of these machine learning and artificial intelligence techniques, you need a lot of data in order to be able to train your model such that the performance of the model is acceptable or it's good. Right? So such data didn't exist back then. So now we have the data, and we also have the hardware to process that data to make, right? And you know, we knew what neural networks were back in the 60s, but it was very difficult to implement a large scale neural network. But now we have the computational power to do that. And that has also sort of led to this whole area of deep learning, which are essentially neural networks, but you know, the number of layers of neural networks is much higher and they're capable of doing much more. Just to give you another example of where we are into, so that was the software part of improvement. We now have better algorithms and so on. We also have much better computing power and hardware. So just to give you an example, so the Cray is a manufacturer of computer hardware and they specialize in supercomputers. And the Cray 2 supercomputer was the most powerful computer in the world back in 1983 or 84. Right? And it was running at a CPU's clock speed of 244 megahertz. And the number of giga floating point operations per second it could do was roughly about 1.9 or 2. Right? And by comparison, the Apple iPhone 4, this is not even the most latest generation, right? I think we are at I don't know, iPhone 12 or 13 or something like that. So this is a few generations ago. That itself runs at a much higher clock speed. And if you look at the number of operations it can do, it's roughly comparable, right? So what has happened is that this machine, which would cost tens of thousands of dollars, and this machine, which is like a few $100s, let's say, they are comparable in terms of their processing power. And in 1984, this supercomputer would have taken up like a small room by itself. Now you can put this in your pocket, the phone, and then they're similar in terms of what they can do computationally. Right? So this has made our life much easier in terms of deploying and adopting AI and machine learning. So now let's talk about IoT and data in itself. Right? So like I was talking about a few minutes ago with IoT, what we are trying to do is we have devices that are smart enough and they are smart enough to decide when they want to generate data and process or send the data over the network. And the whole idea about these IoT devices are that they can be deployed out in the physical world. They're actual physical objects, and they are uniquely identifiable in the sense that we know who is generating this particular data, and we use it for two things. We use it for either sensing, so we want to know what's going on in a particular environment, in a particular machine, in a particular building, whatever it is. And then, based on what we learn or what we understand, we want to be able to take action. So if for just as a very simple example, if I have a sensor in my room, and let's say it's a temperature sensor, and if it feels that the room is too hot, maybe it should turn on the air conditioner, right? That's an example of actuating. And IoT devices tend to be very, very heterogeneous. They can be very small, such as an RFID tag, or they can be something fairly large as an autonomous vehicle or a bus or even an aircraft. They can be fixed in the sense that they don't move around, or they could be mobile, and they could be aimed at monitoring the environment, or they could be on a human body, like the sensors in your smartphone and so on. And the idea is that they are trying to collect information about anything and everything. Right? And this is just an example of, if you're looking at a smart factory, the kind of data that we collect from a factory could be, you could be looking at environmental things such as humidity, moisture. They could be measuring sound, vibration, and so on. They could be looking at things such as processes, flows, and you could look at data that's coming in at a steady stream, or you could be looking at things that you sample once in a while. So there's a whole wide variety and heterogeneity in the data that we generate. And the other thing is, if you look at the data that is being generated by IoT, the amount of data that is generated by IoT has already exceeded that generated by humans and other things. Right? So IoT is right now the primary source of data that's being generated in the world. And if another thing about IoT that we keep in mind is, if I really want to think why I want to deploy IoT, it's not about the things that I deploy. It's not about the sensors that I deploy. That's only to get me somewhere. But what I'm really interested in IoT is the data. So we are actually after the data because that's more valuable. A typical IoT device, it's fine, it helps us do something. But what we are really after is the data. And the value of IoT comes because of what we can make out of that data, how we can analyze that data, and what kind of things we can learn and understand based on that data. Right? So if you look at the IoT value chain, we always start off here, right? We start off by deploying the devices and connecting them to the network. And then these devices will start sensing and collecting the data. And then we have to transfer the data maybe to a cloud-based server or whatever it is, wherever we are storing. So this part is fine. This is the basic thing we have to do. But after this is the point where the value comes in. And this is where we put in data analytics or machine learning or other things. And then we try to understand from this data what's going on. And then once we learn something from the data, now we know what kind of action we can do in order to, let's say, optimize our system, fix certain problems and so on, and then enhance the human experience or the experience of the or the machines or the other applications that are using this data. Just to highlight the point that I'm trying to make here, if you look at this picture, usually when I show it in my class or other things, I tend to ask the students what this picture is about. And since this is an online thing, maybe it's a bit difficult to be interactive there, but maybe just think about what this picture is showing. So a couple of things are quite obvious if you look in the center here. This is like one of those, if you go out in the countryside, you will see these. And these are the towers that hold these electrical wires, right? These are the transmission lines for electricity. But that's not what this picture is about. Sometimes students will say this. Right? So what is this picture showing really? So if all of these yellow and these pink or purple things, these are actually bicycles. These blue, green, these are all bicycles. So about 3-4 years ago, or 2-3 years ago, bike sharing was a big thing in many countries, even in Singapore. And this is actually in China. This is somewhere outside Shanghai. People said, oh, we will have bike sharing applications. So what you need to do is you'll just take your phone. Each of these bikes will have a QR code in the back. You take your phone, you have to download an app and buy some credits. Then you scan the QR code, and then the company will know that you want to rent that bike. There's a lock which will automatically unlock, and now you can ride the bike. Okay? And depending upon how long you keep the bicycle, not the motorcycle bike, but the human powered pedaling bicycle. And depending upon how long you keep it before you return, you will be charged accordingly. Right? And at some point, these bikes were everywhere in China and Singapore and many other places. And so, for example, in Singapore, we had 4 or 5 companies doing this. And pretty soon we would see bikes left all along the roadside and so on. And ultimately, the businesses failed. And this is like a graveyard for bikes. People have just dumped the city government came and collected all the bikes and they've dumped it here. So now the question is, why would so many companies invest in a bike sharing company like this, in companies like this? The answer is that it's not that they felt that they will make a lot of money out of this. It's not that they felt there's a lot of demand for bike sharing and there's a lot of money. The idea is that they really wanted to collect data about the humans who would be riding these bikes. So for example, when you use a bike sharing app like this, the moment you scan and you rent the bike, they know where you are. And then when you drop off the bike, let's say you go from your home to the mall, you drop off the bike there. The company knows that you went from your home to the mall, and on the way back when you come out, let's say you rent the bike again and you go somewhere else, they know how much time you spend in the mall. Similarly, while you are riding the bike, they can track. Right? They know exactly which path you followed. So then they know which. Then they can sell this information, let's say, to businesses and say, so many people go by this. So we think that if you put such and such, so for example, they can go to McDonald's or KFC and say you can open a new shop here and you'll get a lot of traffic. They can sell advertising to they can say that if you put an advertising billboard here, we know a lot of people pass by. So you can gain a lot of information from this. So that's where these companies were after, right? So the whole point I'm trying to make here is that with IoT, the whole thing is about data and how you process the data. But then coming to the processing, when you collect all of these data, usually there are two approaches to how you store and process the data. Traditionally, not traditionally means for the last 10, 15 years, one thing that has been quite common and popular is cloud computing. So cloud computing, probably most of you are already aware, but just in case, what cloud computing refers to is that rather than you owning your computing resources, so this my computing resources implies processors, data storage, maybe even the software that you want to use to run applications and so on. You don't own them. A company owns all of these computing resources and allows you to connect to those resources using a network connection, right? And as a result, no matter where you are in the world, whether you're at home, you're in India, you're in some other country, you are able to access these computing facilities no matter where you are. And the kind of things it does is it allows you to scale very well. So let's say you're a small company now, so you only need a few servers. And if tomorrow your business becomes very popular and you have to scale up massively, you don't have to scramble and then buy 100 new servers. You just tell Amazon or Microsoft, and they will just give you higher facilities or more computing facilities. And also it makes your business a little bit more scalable. You only pay for what you use, right? So those are kind of advantages that we can have here. All right. However, with IoT, one of the things is that depending upon the application, the sensitivity of time is quite important. Previously, historically, a lot of businesses collect data, and after they collect the data, then they analyze. Like some time ago, I was talking about what I call the power grid, trying to understand how much you consume, how much electricity a home consumes or a business consumes, and then they would go back at the end of the month, analyze, and then they say, okay, next month we want to generate so much power. So that's basically dealing with historical data. But with many IoT applications, if you want to be able to react immediately, you are limited by, whether you can use cloud computing or not. Because for you to send the data to the cloud, for the cloud to process, run it through a machine learning algorithm and give the answer back to you, it may be too much, it may be too long. Just to give you an example, consider this where we have a smart traffic light system. So here, these traffic lights, they also have different kinds of sensors. So for example, they can look in all the directions and they can see which way cars are coming. They can also sense if somebody is crossing the road or not, right? So if somebody is crossing the road and then they sense that a car is coming, they can tell the car to stop. But if you think that there's a sensor here who's collecting this, and it's now sending the data back to Amazon Web Services, let's say the Amazon Cloud. Amazon Cloud will analyze it and then send the action back here. that's going to be of the order of almost a second. Right? A second is way too much in an application like this when you would want the car to stop immediately. Right? You don't have that kind of a thing. So in these cases, what we want to do is we want to have something called edge computing. So in the case of edge computing, what we will do is we would set up computers or servers very, very close to where the users are. So the data doesn't have to go all the way up to the cloud. It can be processed in a close neighborhood, and then you analyze the data, and then you send the commands immediately. So the latency would be reduced considerably. But then when you do this, it will create certain new challenges for your artificial intelligence and machine learning algorithms and so on. Right? Just to give you I'll jump into machine learning in just a bit, but just to get you started here. So in the traditional model, what we do is the devices would have collected the data, and then they would send the data to the cloud. Everybody sends their data to the cloud, and then the cloud is the one that processes and analyzes the data and builds those machine learning models. In the edge-based analytics, you don't send all the data to the cloud. Maybe you would analyze them locally somewhat, and then you would learn local models here. And then you will send these local models up to the cloud, and then you would somehow combine these and so on. And so this would be an example of federated learning where you combine smaller models or individual models and then try to come up with a global model. So all of these things are important in the context of IoT. Okay. So now let me just go through a very, very quick introduction to AI and machine learning, and then we'll come to some applications and challenges. Okay. So what is machine learning? Even though I think this is a 5-day course on machine learning, but I'm sure you already are familiar with what machine learning does. It is basically, machine learning refers to the whole body of work that wants to do automated analysis of data. Right? So you just feed data, and the machine is supposed to learn the structure or whatever you're trying to learn, and then come up with answers for you. Traditionally, most of the machine learning and AI work was around biological inspired models, for example, neural networks and so on. But now things have changed quite a bit. And much of this also built upon statistics, as I would talk in just a bit. And the bigger thing is that, many of the things that machine learning tries to do, we also tried to do them historically. But back then, the idea was through the use of mathematical models. So this was the traditional approach. You would get some data, you would try to build a mathematical model for that data. The best you could, if you had to do approximations, you would do approximations and so on. And then using the data model, then you could do things such as prediction and so on, right? But with machine learning, what we're trying to do is we're trying to automate these things, and we don't really care about the model as such. The model is not as important. It's trying to come up with this answer to my question that is more important, right? So the challenge with this mathematical model-based thing is, so we can develop models for applications or scenarios that we can understand, right? That are easy for humans to understand and visualize. But for many cases, it's not so easy, right? So I can write a program very easily, let's say, that will, let's say, multiply two matrices. If I want to do matrix multiplication, I can come up with a program that will do it. But if I want to write a program that will identify or recognize a human face, it's very difficult to say, do this, do that, and so on. So we would like to, so we don't know exactly what is the algorithm to do this. If I ask you to define, tell me how you recognize and how you distinguish between a male face and a female face. You can do it, right? If I show you a picture of a male versus a female, you'll be able to tell this is a boy and this is a girl. But if I ask you to exactly specify what happened in your brain so that your brain was able to tell this was a boy and this was a girl, that becomes very difficult for us to do. Right? So that's where machine learning comes in. The thing may be very, very complicated, but instead of trying to specify the exact thing, the machine learning will somehow try to figure out how to do this automatically. But then we have to help the machine along the way. We help the machine by giving it certain examples that we already tell it that, look, this is a male, this is a female. And by looking at those examples, the algorithm should be able to learn over time. Okay? So this is just an example of, what is easy for humans to do, but then it's very difficult for us to write formal rules for doing the thing, right? So here, these are handwritten examples of numbers. So some examples of 0, 1, 2, 3, all the way up to 9. So if I ask you which ones are 2, so these are 2s, that's easy. And then these are examples that look like 2, but they're not 2. For us, I can tell easily that this looks like this is a 7, this is a 3, or this is a 3. But then if you had to come up with write a program to distinguish, let's say, between this 2 and this 7, it'll be very difficult for us to do that. Right? And instead, we can ask a machine to do that. And the kind of things that machine learning does well is, for example, recognizing patterns. So like I was talking, identifying faces, identifying letters and numbers and so on. We can also use it for different kinds of prediction, for example, using it in stock markets and so on. Another common example of machine learning is for anomaly detection. So here we are trying to find outliers. So we are trying to find, for example, attacks, or we are trying to find cases of somebody cheating and things like that, right? And this is just a difference between statistics and AI or machine learning. Maybe I'll just skip that. Right? So in general, there are 3 types of machine learning algorithms. We can break it up into 3 families. You can do more or less. But you can roughly break it down into supervised, unsupervised, and reinforcement learning. And for all of these 3 things, there are certain things which are in common. So we have to give all the algorithms some kind of data. And then we also usually start with some kind of prior assumption. So we usually begin with knowing what the data is about, or what is the physical phenomena that is behind that data, right? And then the other things is, how do we know what are the fields in the data, how we are representing the data. We also start with some initial assumptions about the hypothesis, or what kind of model we are trying to build, what is the data about, and what is the data trying to uh, uh, yeah. The other things that we also do is we say whether there is any feedback available. Sometimes we have feedback available, sometimes we don't. When it's reinforcement learning, there is usually feedback available. Otherwise, we may not have. And then there are other things, right? So I'm sure the other speakers will cover these in more detail. So maybe I'll just move along to the more interesting. So now let's talk a little bit about supervised and unsupervised learning. In both cases, we will need to have some data, right? So we need some data to train our model. And usually in the case of AI and machine learning, whatever data that we have, we break it up into 2 parts. One part we use for training, and the other part we use for testing, right? So once we have built our model, so the training data is used for building our model. Once we have built our model, we want to know whether it's a good model or a bad model. So we keep aside some of the data, and that data is our test data, right? So now, supervised and unsupervised learning, they mainly differ in the way this data is given to us. In the case where the data is labeled, right? So for example, if you give me pictures of human faces, and you tell which one is a male, which one is a female. Here, I'm giving you data with labels, right? I give you, for every picture, I say it's a male or a female, and then I give it to the machine learning algorithm. So it learns now whether it's a male or a female. And now I give it a picture which does not have a label. I don't tell whether it's a male or female, but the machine learning algorithm should be able to take that picture and tell me whether it's male or female, right? So this would be an example where it learned, or it was a supervised learning, because I told, during the learning process, I told what the labels were. So this is supervised learning. So we have training data. The data already has labels. And this was an example that I was talking about. Let's say I give a database of images, and each image has an output class, male or female. And let's say I give 10,000 such images. I give all of these to my learning algorithm, and then it learns something. And then I have a new image, which is not part of these 10,000. And I don't have a label for this. I will give it to the machine learning algorithm, and it should be able to classify for me whether it's male or female. And that's an example of learning, supervised learning. In the case of unsupervised learning, we just have the data, right? We don't have any labels or anything else. And the idea here is we are trying to find some kind of a description of the data. Okay? And then we will have to come up with some kind of a test metric or an objective to figure out the accuracy of that description. Okay? So let's take an example of this. So let's say this is a supermarket, and here each one of these columns is for one specific user who comes into that supermarket. And then for each user, we see what they buy, whether they buy coffee, milk. So first user came in and bought coffee and milk. The second user came in and bought just some medicine. The third one came in, bought tea, milk, and diapers, and some medicine, right? So there are all these users. So there is no label, nothing. So we just know what, I have a number of users. For each user, I know what are the items they bought. This is the only input I can give to my algorithm. And now I can ask the question, how likely is it that somebody who buys, let's say, medicine also buys coffee? I can ask questions like that, right? And the unsupervised learning algorithm should be able to figure such things, such structure in the data or relationships out. And in the case of a reinforcement learning algorithm, the idea is that we try to develop a system that will improve its performance based on the feedback and the interaction it has with environment. Right? So a common example of this would be a algorithm that learns to play chess. So initially it doesn't know anything, it will randomly pick chess moves.
The permit is not connecting now.
But then it will know by playing the game it won or lost. So you get a feedback at the end of every game you play, and then you learn, okay, this is what I did, and I lost the game. This is what I did, so I won the game. So at the end, you'll be able to learn how to do. So that's a reinforcement learning. So now let's come to some of the applications of these AI kind of things into for IoT. So one example, this is just a specific example, but the whole area is healthcare. So there's a lot of applications of machine learning and IoT in the case of healthcare, where we can have sensors and other devices on a human body, and then whatever data we are collecting can be used for for diagnosing or figuring out health issues and so on. So one example would be blood glucose monitoring using machine learning. Now it's very easy to figure out what the blood sugar level is if I take a blood sample. Right? A common thing is you take a pen, whatever, syringe or something, you make you prick your finger, then you press, a little bit of blood comes out, you give it to a testing device, and then it'll tell you how much glucose it has or your blood sugar level, right? So that's easy. But then the problem here is that, it's physically, it's not good for people, because you have to prick your finger with a needle and then draw blood. So that's painful, and many people are afraid and so on. So one interesting example here is, can I tell your blood sugar level by your sound, the voice, right? And then there are people who are working on such things. And the idea here is that, there's an app on your phone. You turn on the app, you speak something, and then by analyzing your voice, it will tell you what your blood sugar level is. And this is a very, very cool and interesting application. And they have, in this particular work, they had both two versions of this. So in one case, you take the voice samples and then you send to the cloud, and then the cloud has the machine learning algorithm that tells your blood glucose level from the voice. And then in the second case, what you have is ultimately once you have learned these models, they can also be sent back to your phone, and next time you can do this right on your phone itself. And so that's one interesting example. Another big use case of machine learning for IoT is in the area of security, right? So trying to make IoT environments, IoT deployments much more secure. And in this case, AAA stands for Authentication, Authorization, and Accounting. And if you look at historically, most of these, so for example, your cell phone, right, your mobile phone, it does all of these: authentication, authorization, and accounting. So for example, when you have, whether you are a Geo or a Vodafone or Airtel customer, anytime you try to get on the network authenticates you first, make sure you're a valid customer. Then let's say you only have voice services and you try to access the internet, you try to use data, it will see whether you're authorized or not, right? And then it also has to do accounting for billing purposes. So it wants to see how much data plan you have used up, how many minutes you have used up, and so on. So historically, all of this is centralized, where everything is handled by the network core, or there are servers inside the cellular network that handles all of these things. But for IoT, where you have, this works for cell phones because all cell phones are more or less identical. They do two things: they do either data or they do voice. But IoT devices are very, very diverse, right? They can do all kinds of things, and the role they play, that can also change over time. So what you want to do is, in the case of IoT environments, you want your policies to be much more dynamic. You want to be able to learn from the IoT devices to figure out, what should be authorized and what should not be, what kind of behavior should be authorized, what kind of behavior should be unauthorized, right? And then for us, when we want to authenticate our cell phone with the provider, the network operator, we use our SIM card, right? The SIM card information is used to authenticate ourselves. You cannot deploy a SIM card in every IoT device if you are going to deploy millions of IoT devices. That's not possible. So can you do something else? Can you use machine learning to do this authentication for yourself without having to use a SIM card? So these are all interesting applications of machine learning in IoT, right? So for example, we can use machine learning to figure out spoofing attacks and Sybil attacks in IoT environments. We can detect if somebody is launching a denial of service attack, and then so on. We can also use machine learning to figure out whether the IoT device has been infected with a malware like virus or Trojan, and so on. Right? So there are many, many different machine learning algorithm applications that are possible here. Another use case is in the case of retail environments where you have a shop and you're trying to sell stuff to people. Right? In these cases, these shops, they collect a lot of data anyway based on the age of the people, what kind of things that you buy, how much money you spend every time you go. Maybe in a traditional shop where people may not of course, if you go to a supermarket in India like Big Bazaar or whatever, they scan QR code, so they have a record, right? But even in the traditional neighborhood shop, where there is a guy whom you have been buying your groceries forever. By whenever you go, the person just remembers what are the things you buy, so they know what are the things you will buy, right? So shopkeepers, owners, they know your shopping habits and preferences. So now you can use machine learning to figure out things like what is a good pricing strategy, how much inventory you should be keeping for different things, what kind of how you can improve the consumer experience, and so on. And big companies such as Amazon, they actually use machine learning to do, for example, recommendation. So when you go to Amazon and then you search for something, it will also recommend other things for you, right? So that's done using machine learning. Then Amazon has this product called Alexa. This is a personal assistant. So you can speak something into it, and then it'll just process it, right? And it'll understand what you spoke and then act on it, right? So there's a NLP thing in there, natural language processor. That's again machine learning based. Another use case is logistics, right? So logistics refers to supply chain, right? And here we are interested in making sure whatever goods and supplies that are parts, goods, supplies, they should reach the right place or the right person at the right time and the right amount, right? So that's very important. And this is a fairly complex process. You involve, shipping containers, buses, not buses, trucks and delivery vans and so on. And ultimately a human comes and delivers, right? Now in India, Amazon and Flipkart and so on, they're very popular, right? So you know how efficiently they work. And machine learning is behind a lot of their processes. So they can be used for, predicting and recommending future processes. So for example, Walmart uses them for identifying problems in their processes and making adjustments in real time. Honda, which is a car manufacturer, it looks at logistics data that it gets. And then, for example, it looks at, when you go to a website to complain or something, you just enter some text in there or you describe what is the problem. It uses machine learning on those texts that you enter on the website to figure out where the problems might be in the manufacturing process. That's a very interesting thing. The other example here is predictive maintenance. So maintenance is a big issue for all industrial operators, people, companies which operate factories and so on. Maintenance is basically making sure your equipment is working. And usually what happens is you can, of course, go and, if you're a mechanical engineer, you know that you have to do things such as lubricating and checking on things. But usually most of the time you do maintenance after something breaks down. But if you wait for your equipment to break down before you start your maintenance, that's very, very costly. And your system is no longer operational during the maintenance time, right? So the idea of predictive maintenance is you want to be able to predict, let's say 3 days, 7 days in advance that this machine is going to have a problem. So before it actually breaks down, you start fixing it, right? If a ball bearing or something else is going to break down, you replace it before that happens. And the idea here is you can get lots of sensor data, you analyze that sensor data, and then you can predict something is going to happen. So Caterpillar, which is an equipment manufacturer, as an example, they make electrical equipment for use on ships and other things. So they use machine learning to figure out that the amount of fuel, the diesel that was being consumed on the ship, is directly correlated to how many refrigerated containers are there. But when you know these things and then you figure out what is the relationship, then you can optimize your things. Another example is autonomous vehicles, right? And Principal Sir was talking about this at some point. So this is an autonomous vehicle we have on our campus here, drives on its own, takes people across the campus. And this is much more straightforward to understand the applications of machine learning here, right? So the most common example here would be computer vision algorithms. So here there are multiple onboard cameras in this vehicle, and this vehicle would tell you how do you understand from those images whether there's a stop sign, whether somebody's crossing, whether there's another vehicle coming or not. Right? So Drive.ai, for example, is one company which uses machine learning and deep learning techniques to transform the data that we are getting to structured data in order to teach the AV about things and objects and so on. Right? So hopefully that is an introduction to different applications and of IoT, machine learning and IoT. So maybe I'll take another 10 minutes or so to wrap up, and I'll talk about some challenges in these applications. There are many challenges, but I'm going to focus on some security issues in the use of machine learning here, right? The problem is that the more AI and machine learning become integrated with IoT, more attractive it will be for adversaries or hackers to target such things. Right? So if I want to disrupt your IoT-based system, then I'm going to target, for example, the machine learning algorithm that it runs and try to disrupt that. Right? Anyway, IoT has a number of attack surfaces. For example, I could attack it through the communication link and so on. Now, if you're using AI and ML, this leads to additional challenges. And the security challenges here include, we want our machine learning algorithms to be more robust against attacks. Any machine learning algorithm that you develop, how do we do the verification and validation of those things? When we talk about machine learning, there's a whole supply chain. So somebody will generate the data that is being fed in the algorithm. Somebody else creates the models. Somebody else develops the APIs and things like that. Right? So we want to make sure the whole supply chain is secure, and we want to make sure that the whole end-to-end machine learning system is secure, right? So just to give you an example, so there is a training phase for the machine learning algorithm. There's an inference phase. So here you train, and this is where you deploy, right? And then this whole thing runs on the devices that were manufactured somewhere. Attacks could be launched at any of these levels. And I could attack you during the training phase. I could attack you during the inference phase, or I could attack the system while it was in the production phase. So all of these need to be addressed. Now, I will focus now on one specific part of security problem, and this is the problem about adversarial examples. So let me give you an example. Let me talk you through what is adversarial example by talking in the human context. Right? So this is a picture, and I'm trying to attack human perception here, right? And this picture is actually of a cat. Right? So this is quite easy for us to understand that this is a cat. Now, what I could do is I could take some of these pixels in this picture, some of these areas and other things, and I could start distorting them just a little bit. And if I distort it just a little bit, now by distorting means I've added some noise to the picture. Right? I took individual pixels and I added some noise differently. Oops. Okay, so what I did is I took some pixels and I changed the values of those pixels. And as a result, many humans, if they would now say that this looks like a dog, not a cat, right? So that's the whole idea. If there is a classifier, let's say as an example, so here we're trying to classify between cat and dog. Let's say there's a machine learning classifier, machine learning based classification technique. It has been trained on some data. Now, can I do something? Can I generate examples by either modifying them somehow a little bit so that it will be able to fool my machine learning algorithm, right? And there are many applications of that, adversarial applications, and I'll show them to you in just a bit. So this was on humans. Now let's talk about on an actual machine learning classifier. So this picture is the real image from the data set. And this is a washing machine and a dryer on top. Okay? And then this is another image that I have. This is a clean image of that. And what we can do is we can train our machine learning algorithm based on this data. And once we train it, it recognizes that it's a washer, and it gives very high confidence that we will be able to, it gives a 52%, 53% confidence that this is a washer. Now what we can do is we can similarly add a little bit of noise. If I add a little bit of noise, now you see it classifies the probability that it thinks it's a washer has come down to about 0.22 or 0.23. And now it classifies, it says it's more confident that it's actually a safe, not a washer. But at least here we had washer as an option. If I add some extra noise, now it thinks that either it's most likely that it's a safe and a little less likely that it's a loudspeaker thing. Right? So the classifier gives incorrect results with high confidence. So this would be an example of adversarial attack. So now just to before I talk a little bit more detailed in this, so this is my typical machine learning lifecycle. So, I collect data, then I give this data I use this data for training. And at the end, I have my learning model, right? So this is the training phase. And then this model, we give testing data on this model, and then we evaluate the performance, and then we apply, right? So so we have the training phase, and then we have the testing or inferring phase. And the goal of the whole machine learning model is that we want to have some kind of an understanding, or we want to find a model that helps us understand the data. And in the case of a classification, let's say whatever model we are trying to learn, it helps us learn that model, right? So in this example, this is a classification. So I want to find the boundary that will help to separate these two different classes, the pluses and the minuses, right? So during that, if this is the concept or the model that I'm trying to learn, what I do is you give me a number of data points. I want to learn the parameters of that model so that some loss function or the cost function will be minimized. And that's the whole idea of machine learning. And then the way you minimize this, there are many different algorithms, and I'm sure over the next few days, different speakers will go over that. Just to give you an example, if the loss function is continuous and differentiable, we can employ neural networks, and we can use gradient descent to learn the parameters theta. Right? So that's the idea. So that's what we want to do when we are trying to design a machine learning algorithm. What about the attacker? What about the adversary? What the adversary is trying to do is it's trying to reduce the confidence in the system's capability. So for example, if we think about our machine learning algorithm as trying to classify letters, right? So for example, if I'm trying to identify numbers, so this looks like a 1, and if I have trained my model properly, so with 77%, it says it's a 1, 8% it says it's a 0, 14% it says a 2. So of course, I'm going to classify this as a 1. But then the adversary's job would be to somehow generate some or create some disturbance in the input, such that the machine learning algorithm's capability decreases. So after I do this, this 77% becomes 45%, and then these and these become higher. So the system's capability becomes less. And then we can also do other things. So for example, most of our security things, like antivirus and other software, they use machine learning to classify whether something is malicious or benign, whether something is harmful or not harmful. So if I do a misclassification there, and you classify something which is harmful as something which is benign or not harmful, then you will be infected with a virus, right? If somebody is launching a denial of service attack on me, but you misclassify it and say, no, this is okay, then you will not, you'll be subjected to an availability attack and things like that. And when we talk about adversaries, we can also model their knowledge. We can have black box attacks and white box attacks and so on. So in the case of a black box attack, we say the attacker doesn't know much about the model itself, but it's still trying to attack it. And on the other hand, in the white box attack, we say the attacker has access to much more things, such as it may have access to the training data. It knows, for example, you're using a neural network with 3 layers with 5 neurons in each layer or whatever it is, right? So all these things. And in the middle, you have the gray box. So I'll talk a little bit about how we can launch a white box attack, and I'll show you how we can do black box attacks also. And this is just an example of what are the kinds of attacks we can do. So for example, in the training phase, we can launch poisoning attacks. And during the testing phase, we can do evasion or impersonation attacks and so on. Maybe I'll just skip this in the interest of time. So let's look at poisoning attacks, what I'm trying to do with a poisoning attack. In the case of a poisoning attack, so just to start with an example, let's say there are 2 classes and my machine learning algorithm wants to be able to divide this into 2. So this is the true boundary. So in the poisoning attack, what I'll do is I will change the training data in such a way that you will change your decision boundary, and later on, you'll be more likely to make a mistake. So in this case, I will inject a new data here, okay? And I will give it a wrong label. So I will inject a data here, and I'll give it a cross as the mark. So now your decision boundary will be here rather than the earlier one, which was here, right? So previously, for example, a new sample point, here. Previously, a new sample point, if it were here, would be correctly classified. Sorry, no, that's not right. If there was a sample point here during the testing phase, you would be able to correctly classify it. But now, if the same point comes in during the testing phase, you would misclassify it. Right? So that's the whole idea. And then you could also, so this was an example where I tried to poison it by deliberately introducing a sample point. Other ways through which you could do it is, let's say this is my blue and the red are the real data, and that vertical line is the decision boundary between them. What I could do is I could randomly flip the signs or the labels of some of these data points. In this case, let's say I pick 5% of the points, and I randomly flip their position, their labels, and then move them in such a way that you'll be most likely to make mistakes during the testing phase. And of course, if I manipulate more and more of your data, the error that you'll have during the testing phase will also increase. So there are all these ways in which we can do this. Right? And we don't want to get into the mathematics of this. And here's a slide that shows you different kinds of security threats that are possible on these machine learning algorithms. And this is a more formal statement of what we were trying to do in that attack. So what we are given is a trained classifier that takes some data and predicts the class. So for example, you're given a training example, X, and its label. And as an adversary, what my goal is, I want to find another data point which will be very, very close to the original data point, but then the label will be very different. And so that's the goal from the adversary's point of view. And then what we can do is we can specify a optimization problem where I try to find the minimum amount of perturbation that is necessary such that it will be misclassified. Right? And this is what is being done here. So this is an example of an animal, which is a pig. And by following these optimization process, the authors were able to come up with a perturbation, this delta thing. So this is represented by delta. So they were able to come up with a very small amount of perturbation, which when you add to the picture, to the human, it looks no different, right? It still looks like a pig to me, but the machine learning algorithm now classifies it as an airliner. And we could do similar things also here. Instead of adding noise, what you could also do is you could rotate your picture somehow a little bit so that this was a gun or a revolver is now being classified as a mousetrap and so on. So this was a more of a visual example where we were looking at pictures. We can also think of this in the AI machine learning context and the IoT context. So, with smart meters at homes, the meters are the ones reporting back the values of the energy consumption, right? And one of the goals of the power company is to see if somebody is cheating or not, right? If I reduce my power consumption data, I'll have to pay less. So here I will have a machine learning algorithm that will look at your data and it will say, okay, you're cheating or you're not cheating, right? Something like that. So this is again, it's a classifier. It looks at the data and says somebody is cheating or not cheating. So I could use the same strategy here and I could come up with adding a little bit of noise of some kind. So the machine learning algorithm, even though I am changing my values, even though I'm changing my meter reading, the power company will think that I'm not cheating. And that would be an example. And this is another example where we are doing anomaly detection, right, of a turbine. So the idea is you look at the wind velocity that is being reported by the wind turbine, and wind velocity keeps changing over time. And I keep an upper limit and a lower limit associated with everything. And if I see at any point that my one of those upper limits or the lower limits has been exceeded, then I will say that, oh, there's something going on, something has happened, something wrong. And of course, if the wind speed goes too high, there's potential for damage to your wind turbine. So now if I'm the adversary, what I could do is, I could do two things. I could either add noise in such a way that even though it should be classified as an anomaly, you will not classify it as an anomaly, and then your machine will go bad. Or let's say it's not an anomaly, I will add something here so that you will classify it as an anomaly. So you will think that something is happening to your wind turbine and you will shut it down. And as a result, you will run into financial problems or other things, right? You've shut down your option. So these are various attack types and so on. And, since I'm running out of time and I'll talk, maybe we'll just skip this. And the whole idea is, so before I end, let's talk a little bit about how can we defend against such attacks. So there are many things. So for example, when you're trying to prevent poisoning attacks, what you can do is you can do data sanitization. So make sure your data is clean and make sure whatever data you're training with has no adversarial examples. The other thing that you could do here is, while you're training your algorithm, you could train it with some adversarial examples of your own. And as a result, you will enhance the robustness of your algorithm. Right? And if I had time, I would have talked a little bit more about that. So the idea is that during the training phase itself, you inject some adversarial examples with correct label. Right? So these are not real data, but you introduce some fake data, but you give correct labels. So now your system is more robust. And then you retrain your model so that the overall error would be lower. And then, we can think of this as a two-player game and then, think of this as a game theoretic approach, and then we can minimize it and so on. So anyway, so since it's about, how much, 11 o'clock in India, I'll just stop here. And then I would like to conclude by saying that IoT will have a significant impact on all human aspects, and machine learning will play a critical role in trying to understand and analyze the data. And then, but as machine learning becomes more and more important, security of these machine learning algorithms will also be quite important for us. Okay. So I have used many slides from internet-based sources and so on, so they all get a lot of credit for that. So I just want to highlight that. So thank you very much. I hope you find it sort of useful. Thanks.
Yes, sir. Thank you very much for sharing your knowledge and giving your lecture on machine learning for IoT opportunities and challenges. I hope this will be a more informative talk to all of us, and many of the participants also replied it is more informative. And thank you for accepting our invitation in your busy schedules. I am
Thank
also
you very much
happy,
for inviting me.
and I am also happy to see you after 2 years.
Yes,
Yes,
yes, it's been a while.
yes, yes.
Yeah,
Thank you very much,
okay.
sir. We will
Okay,
join with the next
thank you.
wonderful occasion.
Okay,
Thank you for thank
thank
you.
you very much. Yeah, bye.
Bye. Thank you. Uh, this is general information to the participants, and the next session will start by 11:30. Okay, the session will be engaged by Ashwin Vijayendra. Hope you all received the schedule. Okay, as per schedule, 11:30 the session will start. So one of my colleagues shared the attendance sheet through the chat box. Please fill your attendance in session wise. We will take it. Thank you very much. We will join in the next session by 11:30.